Welcome back to the channel where we tackle the biggest questions in science and history. Speaking of big questions, I heard a joke the other day. What's the best part about living on a flat Earth? The horizon. It's a great place to watch your common sense disappear. All jokes aside, the idea that our planet is a spinning blue marble is a foundational truth of modern science. But for those who still prefer the pancake model, today we're bringing out an ancient piece of tech that absolutely, irrefutably, and geometrically crushes the flat Earth hypothesis. The humble sundial. This isn't about blurry photos or high-altitude balloons. This is about math that you can literally measure in your backyard. We're breaking down mnemonics and geodesy, a definitive refutation of the flat Earth model through the geometry of the sundial. Most people think a sundial is just a stick and a plate. Simple, right? But for a sundial to be truly accurate year-round, it needs to be an incredibly sophisticated analog computer. The secret weapon is the gnomon's style, the edge that casts the shadow. For that shadow to move uniformly across the dial, indicating correct solar time, that style must be mathematically aligned to the sky. This requirement, this need for perpetual, consistent accuracy, transforms the sundial into a precision instrument that tracks Earth's movement relative to the sun. And here's the kicker. The geometry required for a functional, accurate sundial inherently assumes a spherical, rotating planet with an immensely distant light source. We measure time using the hour angle, which is the angular distance the sun has traveled since noon. That movement corresponds directly to the Earth's uniform rotation of 15 degrees per hour. The only way to translate that uniform celestial rotation into measurable shadows on a flat plate requires the Earth to be, well, round. We can't talk about shadows and Earth's shape without starting with the goat of ancient science, Eratosthenes, back in 240 BCE. He used a simple stick, a gnomon, to definitively calculate the size of the Earth, a feat only possible if the Earth were curved. His method relied on one key astronomical premise. The sun is so distant that its light rays reaching Earth are practically parallel. On the summer solstice at noon, Eratosthenes knew a vertical gnomon in Cyene, modern Aswan, cast no shadow. Sun was directly overhead, but simultaneously, a gnomon in Alexandria, which was north of Cyene, cast a measurable shadow at an angle of 7.2 degrees. If the Earth were flat and the sun's rays were parallel, the shadow in Alexandria would also have been zero. The observed difference of 7.2 degrees is empirical proof that the ground between the two locations is curved. He then used that 7.2 degree angle, which is 1/50th of a full 360-degree circle, and the known distance between the cities to calculate the Earth's circumference. His result was stunningly accurate, within just 2% of the modern accepted value. The consistency of this calculation globally confirms we live on a uniformly curved body. Now let's get back to the design itself. The math of an accurate sundial demands two things that are impossible on a flat Earth. First, the axial alignment. For a sundial to work through all seasons, the dial must be set parallel to the Earth's rotational axis. In the northern hemisphere, this means it points to the North Star, Polaris. This is non-negotiable for perpetual accuracy. Second, the gnomon angle-latitude relationship. The angle of the style is not arbitrary, it's a direct measurement of your location on the sphere. The angle of the gnomon from the horizontal plane must equal the local geographical latitude, L. In Paris, at 48.8 degree latitude, the gnomon must be slanted at 48.8 degree. This angle is directly tied to how much the rotational axis is tilted relative to your local horizon. On a sphere, the horizon changes continuously as you move. On a flat Earth, the horizon is a single, continuous plane. In that scenario, there is no geometric basis for intermediate gnomon angles between 0 degree and 90 degrees to function. The fact that a sundial built for your city is inaccurate in another city unless the angle is adjusted to that new latitude is a profound functional confirmation of continuous curvature. Flat Earth proponents try to explain differential shadows with the spotlight sun hypothesis. They say the sun is small, local, and orbits close above the disk, meaning its light rays are divergent, not parallel, but this model collapses in 3 catastrophic ways. Failure 1. The impossible fixed gnomon. Under the spotlight. Sun model, the sun is constantly moving its position, horizontally and vertically, relative to any fixed point. For a flat Earth sundial to work, the gnomon could not be fixed. It would need to perpetually tilt and swivel to track that rapidly moving local light source. Fixed-style sundials are therefore a mathematical impossibility under the flat Earth hypothesis. Failure 2. Contradictory solar heights. This is the nail in the coffin. If the flat Earth model were true, using simple trigonometry, triangulation, to measure the height of their localized sun from any 2 points on the disk should yield a single consistent result. But when you use real-world data, say, shadow angles from Brisbane and Sydney, and apply the flat Earth math, the results are wildly contradictory. You get one calculated sun height from Brisbane and a completely different height from Sydney. The sun cannot exist at 2 different vertical heights simultaneously. This geometric contradiction proves the flat Earth model fails the basic internal consistency test required for any valid geometric model. Failure 3. The longitudinal time problem. On a sphere, 15 degree of longitude always equals 1 hour of local time. This is why our sundials and time zones work. On a flat disk, the localized sun would have to travel a vastly longer distance over the outer edge, the ice wall, than over the center, the North Pole, to complete a 24-hour cycle. This would make the sun's apparent speed highly non-uniform, shattering the standard 15 degree per hour system and making an accurate standardized sundial and global time zones completely impossible. If the sundial isn't enough, we have 2 other shadow phenomena that seal the deal. First, the lunar eclipse shadow. When the Earth passes between the sun and moon, the Earth casts its shadow onto the moon. That shadow is always a subtle curve. The only object that consistently casts a circular shadow in every possible orientation is a sphere. A flat disk would sometimes cast an elliptical or a straight-edged shadow, which we never observe. Second, crepuscular and anti-crepuscular rays. These are the stunning sunbeams you see at sunrise or sunset. They appear to converge opposite the sun due to a visual trick called linear perspective, like parallel railroad tracks appearing to meet on the horizon. The existence of this illusion necessitates that the light rays are coming from a source so distant they are practically parallel. If the sun were the nearby, localized spotlight the flat Earth model demands, its rays would be sharply divergent, completely negating this illusion. The light beams themselves provide optical proof that the geometric input for the flat Earth model is empirically false. The sundial is far more than a neutral, dusty artifact. It is a technological device whose design and function are a direct physical expression of one of the universe's most elegant geometric truths. its requirement for a gnomon angle equal to the local latitude, its uniform hourly spacing, and the impossibility of its existence under a spotlight sun model make it an accessible, elegant, and definitive proof that we live on a sphere. The internal consistency of gnomonic science stands tall against the geometrically unstable premise of a flat Earth. Let me leave you with this parable. In an ancient village, a master carpenter built a perfect circular wheel. His neighbor, who only believed in straight lines, insisted the wheel must only work on a flat, perfectly level path. But the carpenter smiled and said, "The wheel's perfection is not in the ground it travels on, but in the truth of its own curve. It works on hills and valleys, over bumps and around corners, because its geometry is consistent with the world it was built to navigate. The sundial is that wheel. Its flawless function proves the curve of the Earth, regardless of what the eye thinks it sees on the immediate horizon." If this breakdown helped you appreciate the incredible science hidden in everyday objects, smash that like button. And if you want to put this knowledge to the test, tell me in the comments. If you travel 15 degrees of longitude east, what is the exact time difference? And how would a flat Earth sundial have to change to account for that? Subscribe to the channel for more deep dives into the science that makes our world work. Thanks for watching, and we'll see you in the next video.